one more here where we're doing zinc replacement. So we're comparing zinc with silver. And you can see silver is very low on the activity series. It's below zinc. So again, below no go. So no reaction for this example here. Okay, the next section, we're doing types of reactions. So if we just kind of look at what's going on, we've got a hydrocarbon and oxygen, so that's called combustion. In the second one, it looks like we have two ionic compounds, and so that's characteristic of double replacement. In letter C, we just have one product, so the only thing that can happen here is it gets decomposed into smaller pieces. And then for letter D, you have two singular elements. So the only thing that can happen is it synthesis, and it comes together to make a product. So to predict the products, this is a bit challenging. You want to make sure you have your ion sheet with the charges to help you. In the first example, you don't need your ion sheets because this is something that's just automatic. A characteristic of a hydrocarbon reacting with oxygen is it automatically makes carbon dioxide and water. But then we'll just have to balance the reaction. So we've got 4 carbons on the left side, and we just have 1 here, so we'll put a 4 here to get 4 carbons on the right side. We've got 10 hydrogens on the left side. We'll put a 5 here to get 10 hydrogens to match on the right side. Okay, so once we have the carbons and hydrogens balanced, this is where we want to focus on the oxygens. And we don't really want to change anything except for this spot here where we're going to put a number to match the oxygens. So on the right side, we have oxygen in both places. We have 4 times 2 is 8, and then we have this 5 from here. So that adds up to an odd number. That adds up to 13. So the strategy is we put half of 13, which is 6.5 here temporarily. And technically that would be balanced, but we need small whole number ratio for the coefficients. So what we do now is we go and we double everything. And don't forget, if nothing's written there, that's like a 1. So that becomes 2. This is going to become 13, and then 8 and 10. And you could go and check that you have the same number on either side at the end, but I'm going to move on to the next one. So in the next one, we have a positive ion, a negative ion, a positive ion, and a negative ion, and the pattern is the positive ions switch places. So instead of lithium with hydroxide, we're going to put iron with hydroxide, and instead of iron with nitrate, we're going to put lithium with nitrate. So you want to think of iron, hydroxide, lithium, and nitrate as being the 4 pieces in this ionic compound. And you really need to know the charges, and we don't necessarily keep the subscripts that are on the left side. So iron in this example is +3, hydroxide is -1, lithium is +1, and nitrate is -1. So on the right side, we're going to need parentheses with a 3 here because the iron was +3 and the hydroxide was -1. We don't need any subscripts for lithium nitrate because they both have a charge of 1. And then we need to balance it. So because of the 3 OHs on the right side, we're going to put 3 OHs here. And then when I put a 3 there, I need to fix the lithium on the right side. And then the other ions should be all set. There's 1 iron on either side, and there's 3 nitrates after putting a 3 on the right side. So that would be balanced. For the next one, we're decomposing aluminum bromide, so we're breaking it into the separate elements. Now, the only thing we have to be careful with that is there are 7 diatomic elements that we need to remember. And the diatomic elements, there's diatomic elements that you want to remember. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. You remember Dr. Huff-Brinkel? So bromine is one of these examples, so you have to remember that we need a subscript 2 with bromine, but aluminum is not, so it does not need a subscript. So then to balance it, we just me to have the bromines match, which would be 6. So I'm going to put a 2 here and a 3 here to get 6 BRs. And then to match the ALs, I'll put a 2 there. In our next example, we're making a compound out of potassium and chlorine, and we don't want to just take, again, the subscripts from the left side. Potassium chloride is an ionic compound, and so we want to check the charges. Potassium's +1 and chlorine's -1, so they go together in a 1-to-1 ratio. And to balance the chlorines, I'll put a 2 in front of the KCl and a 2 on the other side, and that would be balanced. Okay, now we're going to do some stoichiometry problems. Stoichiometry problems are when you have a reaction and you use the coefficients to change from one substance to another. And so if you're given moles of A, you can go to moles of B by using just the coefficients from the reaction. But sometimes they ask for problems involving grams. And when they ask for grams, you have to use the molar mass to get in and out of moles. And so usually the molar mass of the compounds are needed in the problem as well. So when you're given something in these problems, you're given one thing, either moles of grams of something, and you're going to something else in the reaction. So a good strategy is make sure you read it carefully, what the substance is, and write above the reaction what's given to you. So I have 0.07 moles of aluminum carbide. So it's giving us 0.07 moles of aluminum carbide, and it's asking for grams of water. So I'll start with what's given to you, 0.07 moles of aluminum carbide. It's good to write out the substances formula so that you stay focused on when you need to change to something else. So this is giving us moles already, so we don't need the molar mass of the aluminum carbide. We'd only need the mass, molar mass as if you started with grams, because you have to change it into moles. But because it's already in moles, we're ready to do the ratio from the coefficients. So there's a 1 in front of aluminum carbide, so I'll put that on the bottom. And I want to get to water, and there's a 12 in front of it, so I'm going to put 12 moles of water on the top. And then because this asks for grams, I need to go one more step where I change it from moles to grams. And I'm just going to use the molar mass that they gave me here. So for 1 mole of water, the mass is 18.02 grams. So in my calculator, I'm going to do 0.07 times 12 times 18.02, and that gives me 15.1 grams of water. The next problem, they give me aluminum hydroxide to start with, and I have 300 grams of it. So that means I'm going to have to change it to moles by using the molar mass before I convert. And then it asks me to go to aluminum carbide, and it asks for grams. So this is going to be 3 conversion factors where I use the molar mass, the mole ratio, and then the second molar mass. So always start with what's given to you. Start with 300 grams of aluminum hydroxide. Put that over 1. Again, because I'm starting in grams, I need to use the molar mass, which they gave me here. So there's 78.01 grams per 1 mole of aluminum hydroxide. So this got me into moles, which I didn't have to do in number 1. Now I'm ready to convert using the coefficients. So there's a 4 in front of the aluminum hydroxide, so that goes in the bottom. And what I want to get to has a 1 in front of it, so 1 mole of aluminum carbide goes on top. And then the question asks for grams, so I'm going to have to do the molar mass of the aluminum carbide, and that's going to go on top because I want to end up with grams, which is given to me above, which is 143.95. Okay, so in my calculator, I'm going to do 300 divided by 78.01 divided by 4 times 143.95, which gives me 138.4, and that would be grams of the aluminum carbide. Okay, the next problem involves a limiting reactant question. So the problem is that they're giving you moles of each of the reactants, and it's asking how much product it could make. And so you really need to do two separate conversions. So I'm going to take the 13 moles of water and figure out how much product that can make. This is going to be easy because it's in moles and it's asking for moles. So I'm starting with water. And so now I'm ready to go to my reaction. So if you remember, there was a 12 in front of water. So I'll put 12 moles of water on the bottom. And it's asking about the carbon tetrahydride, which is actually called methane, which is here. And that has a 3 in front of it. So I'm going to put 3 moles of CH4 on the top. And so because you're given moles and asked for moles, it's just that one step. And we're going to do 13 times 3 divided by 12. And that gives us 3.25 moles of CH4. Okay, because they give me the other reactant, I have to do the same thing and consider how much the other reactant can make. So I'm going to start with 3 moles of the aluminum carbide. And I'm going to the CH4 again, so I'm going to use CH4 on top. But for the bottom, I'm going to use 1 because there's a 1 in front of it in the reactant for the aluminum carbide. So I'm just doing 3 times 3, which is 9. So when you're given each reactant, you have to consider how much product each one can make. So when the water reacts, it can make 3.25 moles of product, and when the other reactant can make more, it can make 9 moles of CH4. Now when you use both of them together, you can't make 9 because the water can't make that much. So the smaller amount of product of the two is what's called your theoretical yield. You can't make the bigger one because you're not going to have enough of that reactant. So the limiting reactant is water because it makes less product. It's going to get consumed. And the reactant aluminum carbide, which can make more product, is going to be in excess. Okay, and then this last question is just an extension of what we're doing here. So theoretically, if you do this reaction, you can make 3.25 moles of CH4. But then they're telling you that you actually make 49.6 grams of it, like in a lab. And so there's this measurement called percent yield. Percent yield, you want percent yield to be close to 100. That means you did a good job. So it's the experimental value that you get over the theoretical value that you should have gotten times 100. Okay, the only problem is here is the units have to match. So if I know the theoretical yield in moles and they give me the experimental yield in grams, I'm first going to convert the moles into grams. So the molar mass of CH4 is given to me up above. It's 16.05. So 3.25 times 16.05 gives me 52.2 grams. And that's my theoretical yield. So theoretically, I should have been able to make up to 52.2 grams of product, but I only made 49.6, which is pretty close, but not exactly. So I didn't make 100% yield. So I just simply take 49.6 grams and divide by 52.2 grams and then times 100. So 49.6 divided by 52.2 times 100 gives me 95.0% yield, which is pretty good. also did stoichiometry when we were studying solutions. So wherever you see a capital M, that's called molarity. And what we can do is similarly to molar mass, where you can go between moles and grams. We're going to use molarity to get between moles and liters for the solution. So a really key thing here is when you see capital M there, you want to rewrite it as 0.667 moles of that substance, and that's equal to 1 liter. And that will become your conversion factor. So the same will happen down here where you see 1.25 capital M. You should rewrite that above it to help you that there'll be 1.25 moles of H2SO4 per 1 liter of solution. And so part of the conversion, instead of going between grams and moles, will be going between milliliters to liters to moles. So actually this just asks for liters, so it'll make it easier. So you always want to start with what's given to you. So this is something that's extra that's given to us, but you want to start with the other singular thing that's given to you. So in each of these here, don't start with the capital M one, start with the other one. So we're going to start with 2.5 liters and put that over 1. And then again, we can use molarity to get between liters and moles. So because we started with liters, I'm going to put 1 liter on the bottom, and I'm going to put the 0.667 moles of the iron sulfate on the top. So again, we use molarity when we're talking about solutions because they're not a pure solid that you can mass out and measure the grams. It's a way for us to figure out how many moles of the substance we have. So if you have 2.5 liters and this is the molarity of moles per liter, this would give you the moles of the iron sulfate. And so this is just in place of going between grams and moles like before. Okay, once we know this, then we're going to go to what it's asking for. So it's asking us to go to just iron, which is over here. So now we're going to use the coefficients from the reaction. So there's a 1 in front of the iron sulfate, so I'm going to use 1 mole of iron sulfate on the bottom because that's what we started with. And I'm going to put 2 moles of iron on the top because that's the question it's asking for. And then just the last step, because it asks for grams, we're going to look up the molar mass of iron. So if we go to a periodic table, Fe is got a mass of 55.8. So this is just still stoichiometry because you have a reaction, you're going between one thing and something else in the reaction. I'm going to do 2.5 times 0.667 times 2 and then times 55.8. So that gives me a final answer of 186, and that would be grams of iron. So in the next problem, they give me that I have a certain amount of hydrogen gas, 16.9 grams of H2. So I'm going to start with that and put it over 1. The question's asking for what volume of this solution that's needed. So I'm going from the hydrogen, which is a product, to the H2SO4, which is a reactant. But because I'm starting in moles, I have to change, starting in grams, I have to change it to moles using the molar mass of H2. Now H is 1, but this is H2, so it would be a molar mass of 2.0. Okay, then I'm ready to do the stoichiometry where I take 3 moles of H2 on the bottom, because that's the coefficient, put 3 moles of H2SO4 for what I'm looking for. And so this looks similar to, the last section, but now this is like the different part. So we're going to use this, what we talked about before, where we make this molarity a conversion factor. Now, because I had grams cancel out and moles cancel out, right now I have moles of H2SO4. So I'm going to put the 1.25 moles of H2SO4 on the bottom so it cancels out, and put 1 liter on the top. Question asks for how many liters it would be. So 16.9 divided by 2 times 3 divided by 3 doesn't do anything. I'm going to divide by 1.25 and I get 6.76 liters as my answer. So again, molarity is a equivalence between moles and liters, and you want to use that as a conversion factor. Right, here we're just drawing out a picture to show what's happening in the reaction and how possibly there might be a limiting or excess reactant. It's really important that you follow the recipe which comes from the reaction, which is the coefficients. So I'm going to circle to help me 1 nitrogen and 3 hydrogens. So 1 nitrogen, if I follow the reaction, 1 nitrogen and 3 hydrogen makes 2 ammonias. So I'm going to draw 2 ammonias that form as a result of those things that I just circled. Okay, and I'm going to do it one more time where I'm going to circle up another grouping of 1 nitrogen and 3 hydrogens. And as a result of those reacting, that's going to make also 2 ammonias. So these reacted to form those things that I just drew, and then there's the leftover N2 molecule that I should draw. So the limiting reactant would be the H2 because it reacted completely, there's nothing left over. And the excess reactant is the N2, and there's 1 that's remaining. Okay, now we're going to start thermochemistry. So when we did thermochemistry, there was an equation that looked like Q equals mc delta T. And the Q is a measurement of heat in joules. The M is the mass of the substance. The C is called the specific heat. And the delta T would be the change in the temperature. So what we're doing is we have a sample of water here. And the amount of water is important. They say that we have 1,600 grams of water. Okay, what we're doing is we're adding heat to the water so that the temperature goes up. So if it goes from 12 to 20 to 33, that's a difference of 21 degrees Celsius. We want to raise the temperature by 21 degrees Celsius. And so it's asking how much heat would be needed. And so there's this thing called specific heat, and water specific heat is 4.18 joules per gram degree Celsius. And what that would mean is if you had 1 gram of water and you want to raise it 1 degree Celsius, it would take 4.18 joules. But we have more than 1 gram of water. We have a lot, so we'll have a multiple of that. And we also want to raise the temperature more than 1 degree Celsius. So my energy that's going to be needed is going to be a lot more than 4.18. So again, we're going to use this equation. We don't know Q, that's our unknown. The mass is 1,600 grams. The specific heat is 4.18. And then the change in temperature is 21 degrees Celsius. So it's pretty easy. All we're doing is multiplying the specific heat times the mass times the change in temperature, and that will give us how much energy in joules is needed. So 1,600 times 4.18 times 21 degrees Celsius is a really big number. It's 140,448 joules of energy. Another unit of energy we use is called kilojoules. 1 kilojoule equals 1,000 joules. So if we wanted to change this into kilojoules, we could divide by 1,000, and it would be 140 kilojoules. You should be able to use this equation to solve for other variables. If they gave you the energy in joules, you'd plug that in for Q. And they give you the other variables, maybe you'd solve for mass or solve for change in temperature would be your unknown. Every substance has a different specific heat. Okay, this problem here is where we looked at bond energies to figure out the delta H. And when we go to do this, the delta H is always the bonds broken, which is what happens on the left side, minus the bonds formed, which happens on the right side. So a good strategy is to kind of just write out the numbers for each of the bonds. So HCN is 413, and then NN with a triple bond, or sorry, CN with a triple bond is 891. So I'll just add those two numbers up for those two bonds. So 413 plus 891 adds up to 1304 for this molecule. And then HH is 432, but there's a coefficient here. So we're going to do 2 times 432 because we're breaking two of the bonds. So 432 times 2 is 864. So those are the bonds that have to be broken on the left side. So I'm going to add those up together. So 1304 plus 864 adds up to 2,168. So if you remember the potential energy diagrams, that's the going up part. So it's going up 2168. Now to get the delta H, we need to know the going down part, which comes from the bonds that are formed. So let's just make sure that we assign these correctly. So the CH bond is 413, and there's 1, 2, 3 of those. So I'm going to do 3 times 413, and then I'm going to add it to a carbon-nitrogen bond, which is 305, and then I'm going to add that to 2 NH bonds. So an NH bond is 391, but there's 2 of them. There's no coefficient here. If there was a coefficient, I'd have to take that sum of that number and multiply it by whatever the coefficient is. But there's 3 carbon-hydrogen bonds, there's 1 carbon-nitrogen bond, and 2 nitrogen-hydrogen bonds. So I'm going to do 3 times 413. I'm going to add that to 305, and then I'm going to add that to 391 twice. Okay, that all adds up to 2,326. And so we're going to subtract them. We have the bonds broken, that's the going up part, and now the bonds formed. That goes down more than the going up part. So that goes down by 2326. So that means my delta H is going to work out to be negative, which tells me that the reaction is going to be exothermic and it's releasing energy. So 2168 minus 2326 gives me negative 158, and that would be kilojoules per mole. So you just assign the energies per each of the bonds. If there's a coefficient, you multiply it by that. You add up everything on the left side, add up everything on the right side, and it's the left side broken minus the right side formed. Okay, this is another potential energy diagram. I can see that it starts at 80 and it ends up at 160. So it's going up by 80. That would be my delta H. Delta H is the change overall. There's a thing called activation energy. Activation energy is the going up part. All reactions need to absorb energy in order for them to react to break those bonds. So we're going from 80 up to about 240-ish. So 240 minus 80 gives me 160. So the activation energy would be 160. Activation energy is always positive. And because it's absorbing energy, it's an endothermic reaction. Okay, this is using the delta H in a calculation, kind of similar to stoichiometry with conversions. So we need to balance it first because that number is going to be proportional to the coefficients. So I have 1 AL, I have 2 ALs on the right side, so I'll start by putting a 2 there. I'm going to look ahead and see how there's 3 sulfates here, but there's only 1 here, so I'll put a 3 here. And then that gives me 6 hydrogens, so to match the 6 hydrogens on the right side, I'll put a 3 there. So I've got 2 aluminums on either side, 6 hydrogens on either side, and 3 sulfates on either side, so that looks correct. Okay, it's telling me that I'm making 15 grams of this, and it's asking for the energy. So the delta H is proportional to the coefficient mole. So what I need to do here is I need to change the grams into moles first, and then I can use the delta H to change it into kilojoules. So I'm going to have to look up the molar mass of that. So let's just and Google it. So we're looking for the molar mass of Al2 parentheses SO4 parentheses 3. All right, so we're going to go with 342.17. I have another one down below that looks good. We'll just use that. 342.17. 42.17 for the molar mass. Right, so we'll start with 15 grams and put that over 1, and then we'll put the 342.17 grams under 1 mole of aluminum sulfate. Now we have moles of aluminum sulfate, but it's asking for energy or kilojoules. Now the coefficient is important here. So there's just a coefficient of 1. So I'm going to put 1 mole of aluminum sulfate on the bottom. And then we're using this value here, 5,835 kilojoules. So the way the reaction is written is that much energy is released for 1 mole of aluminum sulfate, but I don't have a mole. I have a little less, less than a mole. So this calculation is going to help us like proportionalize how much it would be. So I'm going to do 15 divided by 342.17, and then I'm going to multiply by the delta H, 5,835, and I get 256 kilojoules of energy. Now, there was a negative in the delta H, and you could include the negative here, but that just means energy is released. And so when the question asks for how much energy is released, we don't need to include that negative sign. Okay, this next question is talking about the hydrogen. And instead of using molar mass because it's a gas at STP, what we need to remember is what's called molar volume. Molar volume when you're at STP says that 1 mole has a volume of 22.4 liters. So that's going to be the conversion factor we're going to use. So we're going to start with 20.70 liters. And you know, usually that would have been grams. We use the molar mass, but this is a gas at STP. So we're going to use the 22.4 liters on the bottom so it cancels out, and put 1 mole of hydrogen on top. Okay, that's the part where we change it into moles. Now we're going to use the delta H, but we have to pay attention to the coefficient. So what coefficient is in front of hydrogen? It's a 3. So this number of the 5,000 value is when 3 moles of hydrogen is produced. It's based on the coefficient. So this is going to become a conversion factor for us. We're going to put 3 moles of H2 on the bottom, and we're going to put the 5,835 kilojoules on top. So now we're going to do 20.7 divided by 22.4 to get the moles. Then we're going to multiply by 5,835 to get the kilojoules. But then we need to divide by 3 because that value is for when 3 moles reacts. So I end up with 1,797, and that would be kilojoules of energy released. All right, we have one more problem with this section. Now we're starting with kilojoules, so let's start with writing that 10,500 kilojoules and put that over 1. So that means we can go ahead and use that 5,835 value first, because that is also in kilojoules. And then we want to look to what we're going to. So the question's asking for the aluminum. So we go back up into the reaction and we look at the coefficient that aluminum has in front of it. And that's what that makes that equal to. That delta H value is when 2 moles of aluminum reacts. And so this would give us how many moles of aluminum, but we want grams, so we're going to go one more step. And then we just need to look for the molar mass of aluminum, which is 27.0. So 10,500 times 2 divided by 5,835 times 27 gives me 97.2, and that would be grams of aluminum. So this looks very similar to stoichiometry. We're going between grams and moles when we need to, moles and liters when we need to, but the new part is the idea of this value of kilojoules of energy is proportional to the coefficients in the reaction, and they ask for the energy involved. Right now we have what's called a Hess's law problem, and a good strategy for Hess's law problem is you look for the goal reaction that you're trying to make, and you look at the little reactions that they give you, and you rewrite the little reactions to match the overall reaction that you're looking for. And I like to focus on something that's in the reaction. So I'm going to start with the N2H4. And so if I look in my little reactions, the N2H4 is only in the first reaction, and it's on the correct side, and it has the right number of coefficients. So I'm just going to take that first reaction and I'm going to rewrite it the way that it's there. Okay, and what we'll see is all the extra stuff is going to cancel out. So you can do it in a different order, approach it differently. I like to match up what I'm trying to form. So I see here that I'm supposed to make two NH3s, and the two NH3s are only in that second reaction, and they're actually on the correct side with the correct number of particles. So I'm going to just rewrite that second reaction, and when I rewrite it, I'm just going to try to write it so that the arrows match up with each other. And so as I look at those two reactions, if I sum them together, I would have the N2H4 that I'm looking for, as well as the two NH3s. The H2s are a little bit confusing. You'll see that they're in each reaction, so it'll work itself out. Right now, I can cancel something out. I can cancel out the N2. So you can see the N2 is on the left side here, and it's on the right side here, if we think about the arrows being in the middle. So that's good because we don't want to have the N2 in the overall reaction. So now I'm going to use the last reaction to cancel out the stuff that we don't need. And so I do have to flip this reaction because here I have CH4O on the left side, but I already have it on the left side and I want to get rid of it. So I'm going to rewrite this reaction in the opposite direction. So I'm going to write the product CH2 plus H2 on the left side, and then the CH4O on the right side. Okay, so I had to flip this reaction here as I'm using it. And so now I'm looking for things canceling out. So I have CH4O on both sides. I have CH2O on both sides. Now I'm going to focus on the hydrogen. So you can see 3 of the hydrogens are on both sides. That cancels out. But I have 1 hydrogen left over, which is good because in the overall reaction, I need 1 hydrogen as the reactant there. So I rewrote the reactions. I kept the first one, the second one the same. I flipped the last one. And when I add these 2 reactions up, I end up with this overall reaction that I'm looking for. So now I'm going to focus on the values. So because I kept the first one the same, I'm going to keep that number the same. I kept the second one the same, so I'll keep that number the same. Now I took this reaction and I flipped it, and what we do is we change the sign. So instead of being negative 65, that's going to become positive 65. And then all I have to do is take these 2 numbers and add them together after I made that change to get the delta H for that overall reaction. So negative 37 plus negative 46 plus positive 65 gives me negative 18. So my delta H would be negative 18 kilojoules per mole. Okay. Now sometimes you have to double the reactions or triple the reactions to get the coefficients to match, and just make sure that you do the same thing to the number. So if you double the reaction, you also double the number before you add it together. Okay, we have another example here for Hess's law. So I'm going to go ahead and look for the H2SO4 somewhere in the reaction. I need it on the left side. So I see it in the first reaction, but it's on the wrong side. So I'm going to take that first reaction and I'm going to rewrite it so that the products are on the left side and the reactants are on the right side. Okay, so I reverse this reaction here. And so now I have the H2SO4 that I'm looking for on the left side. And now I'm going to go and look at the next reaction. So, and the next reaction has SO3 here, which is what I'm looking for, and it's on the correct side. So I'm going to go ahead and copy that next reaction the way that it is. H2S plus 2O2 makes SO3 plus H2O. And I'm going to highlight the SO3 to match the product. Okay, so we can start to look for things that cancel out. So I can see that H2S is on both sides and 2O2s are on both sides. Now I do need the water on the right side, but there is a little caveat here. The water here in this example is a liquid, and in the overall reaction they want me to have it as a gas. So I'm going to use the last reaction to make that change. And because the liquid's on the right side, I want it on the left side to cancel out. So I'm going to use that reaction the way that it is. So I'm going to use the last reaction there with water as a liquid turning into water as a gas. And we can see that the water as a liquid will cancel out, and we'll highlight the water as a gas because that's what's in the overall reaction that we're looking for. So again, this one was pretty easy where we kept the second two the same, but we reversed the first one. So because I reversed the first one, I'm going to make it positive 233.5, 235.5, and then I'm going to keep the other ones the way they are and add them together. Make sure you're careful with the signs as you do this. So I have positive 235.5 plus negative 207 plus positive 44 gives me positive 72.5. And that's kilojoules per mole.